that you begin to run into in this unit and in this class, you're going to start to ask yourself, how are we supposed to know that? You are going to feel violated. You are going to feel betrayed. You are going to feel like the world is conspiring against you because you are being asked to know things that you were not directly taught. Welcome to college. But guys, that said, realize that the stuff that you're going to learn this year, when it really, really counts at the end of the year, you are going to look back in amazement and go, dang, how do I know all of this stuff? So guys, understand, you're in process. The only thing that you can do to screw this up is to read a question like question number 3 and get all indignant and go, how am I supposed to know this? This is stupid. I'm going to learn from the things that you're doing to learn. So, with that said, question number 3. It says, use the following molecular representations to figure out if they're weak, strong, or non-electrolytes. So guys, do non-electrolytes dissolve in water? We are reviewing. Do non-electrolytes dissolve in water? Yes. What do they not do in water? Ionize. Give me an example of a substance that does that. Sugar. Not salts. Guys, salts either dissolve or they don't. And if they do dissolve, they break into ions. For now. And then guys, strong electrolytes dissolve and completely ionize. Weak electrolytes dissolve and partially ionize. So with that said, are we looking down? Is it the molecules down below? All right. So guys, let's talk. Again, very fairly, your response to this could be, how are we supposed to know that? But let's talk about what you need to know. Guys, again, red is oxygen, black or gray is carbon, white is hydrogen. And so what we have here is a molecule, letter A, where we have a carbon bonded to an oxygen, bonded to an oxygen, bonded to a hydrogen. Now, and there's another hydrogen right here. Okay, thank you. All right, so guys, as we look at this, we first of all need to realize that we have not completed octets. And when we complete octets, oxygen has got 6 valence electrons, so oxygen loves to form 2 bonds. The other spaces are filled with unbonded electrons. Carbon, on the other hand, loves to form 4 bonds. That's why we are carbon-based life, because 4 bonds is a maximum number of bonds, and it allows for maximum complexity. Carbon in this example only has 3. So where is the carbon going to bond? Well, it can't bond to the hydrogen because hydrogen's one and done. So the other bond is going to form here, and it's going to be a double bond. Again, oxygen likes to form 2 bonds. And then we've got unbonded electrons here, and this is then the Lewis dot structure for this molecule. Now at this point, does this look familiar? Remember this? See the connection? If the hydrogen were gone, this would be acetate. With the hydrogen there, what is it? Acetic acid. It's an acid. It's a weak electrolyte. Guys, this is the same. You've got, and I need to sort of get out of the way, but you go hydrogen, oxygen, carbon, double bond oxygen. Guys, that is actually what is called a carbonyl group, or a carboxyl group. And we'll talk more about this later in the year, but the same thing that makes this a weak acid makes this a weak acid. That would be a weak electrolyte. How are you supposed to know? Now you know. So then guys, looking at the next one, you really should have been able to look at that and figure out that's nitric acid. You've got a nitrogen bonded to 3 oxygens. That's nitrate. Tag a hydrogen on there, and you've got nitric acid. That's a strong acid. Then, guys, looking at this next one. It's a big old gobbledygook of stuff. If you pull it apart, did they give you the other hydrogens? They do. Guys, if you pull it apart, it actually looks like this. This is not the same as this. You'll notice that these molecules both end in OH, and this also ends in OH. The difference is this. Here we've got an OH attached to a carbon and attached to a double bonded oxygen in both cases. We do not have that here. Therefore, this is a different kind of compound. Do any of you know what it is? It's an alcohol. Guys, this is what alcohols are. Alcohols are long chains of carbons that then have OHs bonded to them. This is what is called ethanol. This is the stuff that is in beer and wine, and it's the alcohol that gets you drunk, you drink. So this is ethanol, but this is an alcohol. Does alcohol dissolve in water? You bet. Does it ionize? Not at all. This would be a non-electrolyte. Yeah? Yeah, it is very much the case. So alcohols, in this class, it's always terrifying to say always and never, because the minute you say always and never, if you can come up with one exception, you're wrong. You'll learn this when you get married. Never say to your wife, you always do this, because she'll immediately give you one example of when she didn't, and now you're wrong. Never do that. So guys, never, always, and never, but, all right, shoot. But in this class, yes, alcohols, the word that we use is tend to. Alcohols tend to. They do not ionize. So in our world right now, alcohols will be non-electrolytes. Understand, there are some substances that can ionize alcohols, but those are a whole different class of chemistry that we don't need to talk about in here. Yeah? Yeah? Mm-hmm. Okay. Keep.
If they're not like strong acids or
yeah.
salt,
yeah.
they will not be a strong electrolyte.
You know what, Santiago? That's brilliant. And you know there's a name for that. It's called process of elimination. If it's not this, and if it's not this, it's got to be that, right? I love that. That's beautiful. Yeah, that's...
I get it.
Uh-oh.
One in the C, non-electrolytes.
Which one did you get wrong? The A. And that's probably because you didn't have enough of an understanding to understand about this. The idea that we've got a carbon double bond, carbon single bond, which then creates this carbonyl group, which is then a weak electrolyte. But now you know. Okay. Yeah, please, man. It's a base. Yeah. Right. Sure. Sure. Yeah. So. Mm-hmm. Absolutely. So let's talk about the good and the bad about what's going on in your brain, okay? So the good is you are trying to bring experiences to bear on a new situation, right? And you're talking about size, and you're talking about complexity, and you're talking about OH groups, and you're bringing all of these things that you know, and you're trying to use those things to make sense of something new. That's the good part. The bad part is you didn't know enough. Right? So you needed to fill up your toolbox with enough tools that you could bring the proper tools to bear on this idea. So your process is awesome, but the actual outcome of the process is going to get better every single day as you learn more and more and more. And again, by May, you're going to be like, good night, how am I even doing this stuff, right? So don't ever give up on the process. And realize that as the year goes on, we're going to fill in the gaps, and all of a sudden those are going to marry together really, really well. It's a good thing. So guys, what else do you want to talk about? How did you guys do on writing net ionic equations? Do you mind if I sort of take the lead for a second? Because I'd like to talk with you maybe about number 24. And maybe even number 23. Conveniently, they're all there together. Guys, writing net ionic equations is going to become something that you do, I don't know, instantly, immediately. That I understand that right now, writing net ionic equations is, come on, let me move you. Guys, writing net ionic equations is many times the last in a multi-step process. You're figuring out the reactants and products. You're identifying spectators. You're getting rid of those. You're coming to net ionic equations. Guys, let me lay a little nugget in your lap that I think you're going to find will help. And this is all about solubility rules. Guys, you need to gather up a little corral, if you will, of ions that you know always dissolve in water. And if you have a little corral of ions that you know always dissolves in water, you now have a corral of what kind of ions? Spectators, right? So guys, if you've got that corral of soluble ions, you now know your spectators. And if you know your spectators, you now know the other things, which then become the pieces that make up the net ionic equation. Let's say that again. If you have a corral of ions that you know are always soluble, those are always spectators. If you can identify the spectators, then process of elimination, all the other stuff is what goes in the net ionic equation. Does that make sense? So with that said, guys, do you want to grab your table 4.1 summaries? And let's talk about the ions that are always soluble. You guys notice this? Oh, here. Yeah, guys, sodium is always soluble. Again, as Josh got us thinking, be careful with always and never, right? But guys, again, I'm not really good at memorizing every little detail. Close enough for me is close enough. Are there some salts that contain sodium that don't dissolve in water? Just a minute, Chase. Some. But I'm okay with that. I'm going to be okay getting a couple of these wrong. It's not worth it to me to memorize everything, so it's close enough. You guys understand this, right? You're not shooting for 100% on the AP test. So guys, it's not just sodium though. Sodium is a part of a bigger group of elements, ions, that also all dissolve. All these dudes. Guys, all the group 1 metals are always spectators. Really always? No, but close enough. All of the group 1 metals are always spectators. What are others that are always spectators? Nitrate. Acetate, which I don't even believe is represented on the screen. But no, let's write it down. That's not a bad. That's good, because you're bringing in other ideas. Ammonium. Guys, this is one that we really didn't talk about yet. How do we know that ammonium is always soluble? Well, if you look at table 4.1, you'll notice that it's broken into 2 parts. The top is stuff that always dissolves. The bottom is stuff that never dissolves. But in the list of stuff that never dissolves, you'll notice that the exceptions always include ammonium. Guys, ammonium loves to dissolve in water. If you still have your yellow solubility sheets, and if you look up ammonium, you're going to see S's all the way across that horizontal row. Guys, ammonium is another thing that always dissolves in water. What else? Did we say nitrates? Yeah, nitrates. But then, guys, the other thing that I would do is this. I would also make myself a little list of stuff that doesn't dissolve in water. And for me, that list includes silver, lead, and mercury. And then it also includes the group 2 metals above calcium, magnesium and beryllium. But I can remember that because I know what the strong bases are. I know that the strong bases are the hydroxide salts of the group 1 metals and then the group 2 metals, calcium down. So these guys up here don't like to dissolve in water, which is also why they don't form strong bases with hydroxide. So guys, with that said, now let's go up here to the screen. So if we want to figure out, like looking at number 24, if we want to figure out what our net ionic equation is, we can start to take some of these ideas. Because I know ammonium is always going to be soluble. That guy's always going to dissolve in water, so it will always be a spectator. But then I also know that all all precipitation reactions are double displacement. So I know the ammonium's going to hook up with the sulfate. But I know that's going to dissolve in water because of the ammonium. So now I can assume that sulfate is also going to be a spectator, and I don't even need to know the solubility rules for sulfate. Because I know ammonium already dissolves, I can then rule out the sulfate. These are, in fact, our spectators. And once I get to that point, the only thing I have left is chromium and carbonate. And those are the things that go in my net ionic equation. Then I need to know their charges. Chromium's +3, carbonate's -2. That meets up at 6. So I need 2 chromiums, 3 carbonates, balance the equation, you're out the door. So guys, very, very quickly, you're going to be able to look at something like this and go, that's gone, so this is gone, this stays, put them together, there's my net ionic equation, and you're not going to need to write down any of this, you're just going to immediately go there. Yeah? No, because you can still balance it. And here's why. So chromium can be +2 or +3. How do I know which one it is? Well, I work it backwards. Sulfate's -2. -2 times 3 is -6, so this is +6. +6 divided by 2 is 3. So I know that chromium's +3. Then I know that carbonate is -2. Then imagine that these aren't here. Where do +3 and -2 come together? 6. So how many chromiums do I need? 2. How many carbonates do I need? 3. And then I just carry these numbers back over there to make it balance. I don't need this let me do it differently. I don't need this in order to figure out this and this. All I need to know is the formula of the product, and then I can balance the equation from there. So guys, again, there are things that you will increasingly wrap your arms around as we get deeper and deeper into this stuff. With that said, on the test, guys, we're probably looking at the first unit test either at the end of next week or the beginning of the week that comes after Labor Day. Guys, on the test, I will ask you to write the complete molecular equation. I will ask you to get rid of spectators, and then I will ask you to write the net ionic equation. I want to see that thought process at this point with the understanding that very quickly we're going to not need to do that, and we're just going to cut to the chase. We okay? Chase, you've been waiting. I'll get it. Cut to the... Hold on. We got to do this. Cut to the chase. That's all I got. That's my best stuff. You're squishing my soul. That's some of my better material. I know it's that bad. Okay, sorry, you wanted to talk about chemistry. What? Oh, about ammonium. So ammonium is a spectator. So guys, I would like to put this to rest. Are we okay to move forward? Okay. So guys, let's get this recorded. You need note-taking materials. What do? I pause. Done. And then over here, and then over here, and then over here, and then over here, and here, and there. All right, guys, today we're going to take the next step into Chapter 4, and we are going to talk about acid-base chemistry. Understand that we did this last year, which is not to say that I expect you to know all of this, but it is to say that some of this we will actually be able to treat as review, and we'll talk about that as we go. Guys, at the end of this, however, we're going to come to some information that is going to be new and important. And it's probably, for some of you, going to turn into some of the stuff on the test that quickly turns into a how are we supposed to know that? Guys, at the end of the day today, we are going to be introducing ourselves to some general forms of acid-base reactions that you just need to know. So some of you, the question is going to be, how are we supposed to know that? And guys, the answer, it's nice. The answer in this case does not just need to be because you need to know it. Because on, what's today, Friday, Tuesday? We're going to go and do all these reactions in lab. So for now, we're going to introduce ourselves to these general reactions. And then when we get together next week, you are actually going to be able to go over to lab and carry these out, which is wonderful preparation for the test. All right, so guys, getting started. Yeah, that's fine. Yeah, I mean, if you're not going to come, I mean, just watch the screencast if you need. Like, can you get down there on your own?
Yeah.
You're okay? Okay. So guys, it goes like this. Please don't write any of this down, but I want to put this in context for you. Here's where we are. Here's where we're going. The beginning of the unit, we went through Chapter 3 at breakneck speed, and we got our arms around stoichiometry. Then, guys, we are now in Chapter 4 where we're talking about aqueous chemistry, and we understand that aqueous chemistry happens in the context of water. As we've done this, last time we talked about precipitation reactions. Today we're going to talk about acid-base reactions. Tuesday, when I see you next, we're going to go over redox chemistry. Then when I see you on Thursday, we are going to wrap up the unit by talking about titrations. And then, guys, following that, the next Tuesday, because there's no school Monday, that's when your test is going to be. Would it be helpful to do that again? I hadn't really had, so let's put this together. Today, Friday, acid-base. Then Tuesday will be redox. And then Thursday will be titrations. And then no school that Monday, so then the next Tuesday. So guys, the Tuesday coming back after Labor Day will be your first unit test. Okay, so guys, with that said, we've got to be really, really clear about this. We are about to go over acid-base chemistry. But guys, are you familiar with the concept of a 30,000-foot view? Have you ever heard that expression before? If you haven't, get used to this. So guys, when we talk about a 30,000-foot view, what that means is we are going to conceptually fly over this from a very high vantage point, and we're just going to get a general sense of what's going on down there on the ground. We're not going to get into real detail. We're not going to get into specifics. We're going to get a 30,000-foot view. In February, we're going to get down in the trenches and we're going to spend 5 weeks on acid-base chemistry. So we're going to learn just enough today that we can talk about this until February and have a common idea of what we're talking about. But guys, understand, this is crazy fascinating stuff, and we're going to do a super deep dive around Valentine's Day. So, I know. So, guys, with that said, the way that we are going to address this is we are going to tie these ideas back to the bigger ideas, which are all about aqueous chemistry, ions in solution, and also solubilities. So with that said, guys, here's what we need to agree on. Acids are substances that ionize in water to form hydrogen ion. Because I'm going to just ask this as a question, and if you don't know the answer, I'll draw you the picture. What is a hydrogen ion? It's a proton. Does that make sense, or should I draw you the picture? Let's draw you the picture. Guys, hydrogen is element number 1 with a mass of 1. So, a hydrogen ion is 1 proton. I'm sorry, that's not true. A hydrogen atom is 1 proton and 0 neutrons in the nucleus. And then zipping around that nucleus, we have 1 electron. This is a hydrogen atom. What do we do in order to make it a hydrogen ion with the +1 charge? Get rid of the electron, and now what we're left with is a proton. Does that now make sense? Okay, so guys, when acids release these hydrogen ions, these protons, what happens then is it increases the concentration of hydrogen ion in solution. That's pretty straightforward. Now guys, at this point we need to talk about the different ways that this can happen. There is a whole class of acids that we call monoprotic acids. You want to hazard a guess as to what that means? What do monoprotic acids do? Release 1 proton. So guys, monoprotic acids are acids that release 1 hydrogen ion into solution. One of your personal favorites is your good friend hydrochloric acid. That releases a hydrogen ion and a chloride ion. But guys, there's a whole other class of acids that we need to introduce now, so that we'll do all the math of these in February, but we're going to talk about them conceptually right now. They're called polyprotic acids. Not surprisingly, they release more than 1 hydrogen ion. All right, guys, winner gets a lifesaver. What is the only polyprotic strong acid? Who said it? Guys, there's only 1 polyprotic strong acid, sulfuric. Can you run through the list? HCl, HBr, HI, all monoprotic, HNO3, nitric, monoprotic, HClO3, monoprotic, HClO4, monoprotic, H2SO4, polyprotic. So, guess what we're going to do? Draw a beaker. Guys, just get used to this. We draw lots of beakers. Draw a beaker. And guys, in your beaker, add some water. Why? Because this is chapter 4. It's aqueous chemistry. We got to have water. And then, guys, here's what I'd like you to please do in your beaker. Write down sulfuric acid, H2SO4, and then please write down the balanced equation that represents 1 of those hydrogens coming off. I will be very, very surprised if any of you get this completely right. Only 1 of the hydrogens. I'm going to move this over so I have a little more space. All right, so H2SO4, one hydrogen comes off, and then we're left with this. Now, if you get that? Still wrong. What are we missing? Charges. Hydrogen is positive, and this is negative. Did any of you get that? You don't get another lifesaver. I'm glad you got it. Now, guys, please. Hydrogen, one of the seven what? Oh, brilliant. Guys, no. Let's talk about this. This is a great question. So, guys, check this out. When you said the seven, I was thinking strong acids. You threw me a curve. You're talking about the diatomics. So, guys, look. Iodine, bromine, chlorine, fluorine, oxygen, nitrogen, and hydrogen. Do you remember that those are the diatomics? Do you remember that that means that they bond to each other when they have nothing else to bond to? Yeah? Here's the trick. This isn't hydrogen. No, it's a proton. That's not the same as hydrogen. When we say hydrogen is diatomic, we mean hydrogen atoms are diatomic. So if you have a proton with an electron zipping around the outside, and then you've got another proton with an electron zipping around outside, two hydrogen atoms, they will single bond together and make a diatomic molecule. This is not hydrogen. This is hydrogen ion, and those are radically different. A hydrogen ion doesn't even have any electrons to covalently bond. That's a proton. So yes, hydrogen is diatomic, but that's not hydrogen. It's hydrogen ion. And guys, I know that in your limited experience in chemistry, you're like hydrogen and hydrogen ion, the only difference is a plus sign. They got to be close. They couldn't be any more different. The only thing they have in common is they start at the same place, but when atoms become ions, their behaviors change radically. I'm so glad you brought that up. So, guys, are we good there? Now let's learn a little bit more. You okay, buddy? Okay, sounds good. Watch the screencast. So, guys, while Kyle's getting settled, we can do this really carefully. Watch. Tell me the name of SO4. Sulfate. Guys, when you add a hydrogen to that, its name changes to bisulfate, just like bicarbonate. So carbonate is CO3 minus 2. Bicarbonate is HCO3 minus 1. So guys, anytime you see the prefix bi in front of the name of a polyatomic, it means that it has a hydrogen attached to whatever that ion is. And notice that its charge is different. Carbonate is minus 2, bicarbonate is minus 1, sulfate is minus 2, bisulfate is minus 1. So are you okay with all this chemistry? Because it doesn't stop there. Guys, what happens now is this. The HSO4 minus the bisulfate loses another hydrogen. Bye, Kyle. Hope you feel better. Guys, it loses another hydrogen. So let's do this together. When this loses a hydrogen ion, now what's left? Sulfate. But guys, that's not the complete story. What's wrong in this expression?
How did sulfate regain a charge?
It didn't. It lost a proton. And when you lose something that's positive, your charge becomes more negative. Yeah. Guys, what's wrong with this? You know enough to know. Chase, you're a genius. Guys, you know the exhaustive list of the 7 acids that completely ionize, and this ain't one of them. This is not a strong acid. This is a weak acid. So now, guys, what I want you to do is this. You understand that sulfuric acid is what we call battery acid, right? So if I hand you a bucket of battery acid, what's in there? Circle the things in your paper that exist in a beaker full of battery acid. What's in there? Circle the things that are present. And then, guys, gently cross out the things that aren't. So let's do this. I'm going to switch colors. So guys, in a bucket of sulfuric acid, is there any H2SO4? No. This is completely ionized. It is a strong acid, and it is completely giving away hydrogen ions. Is there any hydrogen ion? It's an acid, of course there is. Now, what about the bisulfate ion? In order to answer that, we know that bisulfate is formed by this reaction. So preliminarily, we're going to say yes, there's bisulfate ion. But to fully answer the question, we've got to go down to the second reaction. As a result of this, does all the bisulfate ion break apart? No. So yeah, there's bisulfate ion. But in addition to that, some of the bisulfate breaks apart and it forms hydrogen ion and it forms sulfate. So in a bucket of battery acid, you have a lot of protons. You've got some bisulfate ion and some sulfate ion. The only thing that you do not have is the H2SO4 because that completely breaks apart. Does that make sense? Is that okay? All right. So guys, this was also then a great introduction to strong and weak acids. This is a strong acid. This is a weak acid. Does that make sense? Is that okay? By the way, guys, if you tag a sodium onto this, you end up with sodium bisulfate. And for those of you that have hot tubs, that's the stuff that you dump in your hot tub to make the pH go down. You actually are adding sodium bisulfate salt. The sodium is a spectator. The bisulfate dissolves into your hot tub water, and it gives away some hydrogen ion, and that makes the pH go down. This is actually the salt that you buy. It says pH decreaser on it. This is actually the salt that you use to make your hot tub more acidic. I'm convinced that in order to actually own a hot tub, you have to have a degree in chemistry. So, you guys good on all of this? All right. So, guys, let me clean up my mess. And let's allow this to now become visual. Now we need to do something important. Listen carefully.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen.
Then we need to give this girl a name. All of the videos that we watch in here are narrated by this same woman, and so every year we give her a name. Let you listen to her again, and then we'll decide on a name.
Chloride is an example of a
Last year she was Susie.
common and important acid. When hydrogen chloride gas
For some reason, she doesn't sound as fun to me as a Susie. She seems serious.
dissolves in water, it forms hydrochloric acid.
Sorry, because then when we do that, all of our phones are going to light up.
Hydrogen chloride is very soluble.
All right, guys, we need a name. What do you think? Go ahead. That's hard to say, though. Kathy?
Kathy, I was thinking Kathy too.
Can we, Bethany and Kathy are kind of like, can we go Kathy?
Kathy.
Is anybody offended by Kathy? Is any of your names actually Kathy, or your mom is Kathy, and then this is going to become personal? All right, Kathy it is. So guys, we are going to allow Kathy to take a swing at helping us better understand acids.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte.
Does all of that make sense? Questions? Strong electrolytes, Strong acids.
Nitric acid is
Strong or weak? Let's keep going.
another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution. Like hydrogen chloride, nitric acid is a strong electrolyte.
And guys, again, I know you understand this, but water is missing from the picture, right? There would be water molecules surrounding the nitrate, and then this hydrogen ion would actually be bonded to a water molecule, forming hydronium. We leave it out of the picture, but that's actually what's going on.
It is a strong electrolyte.
Weak or strong? Yeah, this is acetic acid. It kind of looks like a poodle.
Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it is not completely ionized. It is therefore termed a weak electrolyte.
What's going to happen when I hit play? They're going to go back together.
Or weak acid.
Guys, understand the only misconception in this animation is that this acetate ion does not necessarily recapture the proton that it initially lost. There's protons everywhere, and it could capture a proton that came from another molecule. But it does, as equilibrium goes, work back and forth between the two. Good? All right. So guys, now let's shift gears and let's talk about bases. So as we talk about bases are substances that accept hydrogen ions. You may remember from last year the difference between the Arrhenius and the Bronsted-Lowry definitions. The Arrhenius definition is it releases hydroxide. We are not going to use that definition. It's too limiting. We use the Bronsted-Lowry definition that says that bases accept hydrogen ion. So guys, when this happens, it increases the concentration of hydroxide in solution. So now you're going, wait a minute, how's that work? If a base accepts hydrogen ions, why does the OH concentration go up? Kind of. Guys, what's the title for this chapter? Aqueous Reactions. What does aqueous mean? Water. And guys, water is H2O. Or water, as a Lewis dot diagram, is this. Or, if you want to think about it this way, water is hydrogen hydroxide. What does the hydrogen make water? An acid. What does the OH make water? A base. Guys, we live in this mystical, magical universe where the most plentiful substance on the planet is also perfectly an acid and perfectly a base. You are free to believe that that happened by chance. I find it creative. It's pretty cool, but that's all I can say. So guys, the idea is this. If a base accepts hydrogen from the water that is always around, because there's always water around, because that's what acids and bases do. If we accept a hydrogen, we're left with an OH, and that's how these two ideas come back together. But it can happen differently. So let's bring to bear the things that we know. Guys, metal hydroxides are bases. If that metal is a group 1 or group 2, heavy group 2 metal, these are the strong bases. So guys, how does this work? Please write in your notes the balanced equation that represents the dissociation of sodium hydroxide. In your notes, please write the balanced equation that represents the dissociation of sodium hydroxide. So guys, we've got this. Sodium hydroxide breaks in water into sodium ion and hydroxide ion. So guys, from the sodium hydroxide salt, we now have an abundance of hydroxide ion. Miss Call's printer doesn't work, so now she prints stuff in my room. I think we should wait for her to arrive. No, we shouldn't. That's what we need, yeah. We've been expecting. We should lock the door and make her knock. Where do you think she's going to come from? Yeah, she's tricky that way. Hello? Hello? What do we say?
Well, thanks, guys. I announced my coming.
Oh, shoot. All right. So, guys, obviously, from the dissociation of hydroxide bases, metal hydroxide bases, we very clearly see how we satisfy the second thought, right? That's where our hydroxide comes from. But what about the first thought, accepting hydrogen ions? Well, guys, we understand that this is happening in water, and when this happens in water, this hydroxide can take in a hydrogen from the water. But when it does, what else does it make? Hydroxide. So we don't talk about it. You get the idea? That this is happening in water, and the hydroxide ions that come off of our base, these hydroxide ions can attack water. And when they attack the water, they can pull a hydrogen off the water. But when they pull the hydrogen off the water, what else do they make? Hydroxide, right? And as a result, we don't talk about it because it doesn't change anything. But what about these? These are what are called the non-hydroxide bases. There's one that you need to know. It is ammonium. Sorry, ammonia. That was bad. Ammonia. NH3. So, how does ammonia fit the definition of a base that we see at the top of the screen? And guys, I like to think about this doing it the opposite. With something like NaOH, it does this, that then lets it do this. With NH3, it does this, which then lets it do this. Let me show you what we're talking about. NH3 is in water. NH3 is a base. That means it's going to take in hydrogens, ions. When it does, it makes NH4+. The hydrogen came from the water. When we steal a hydrogen from water, what's left? The OH. But this is weak, so it's a double-headed arrow. This is how we satisfy both of these requirements when we're talking about weak bases. The base steals a hydrogen from water that has to be there because all acid-base chemistry, until you get to your sophomore year in college, is always in water. And so, guys, because this is always in water, this steals a hydrogen from the water, you're left with OH, and then it all fits together. Is that okay? Okay. So, guys, with that said, I think the only right thing to do is talk to Kathy. Shoot. Kathy. She's back. Kathy's mad at us. The downfall.
Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common bases.
Did you notice the list?
When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base. It is also, of course, a strong electrolyte.
Do those things jive with your understandings? Okay, let's do that.
Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form the
Yeah? But now what's going to happen when I hit play?
ammonium and hydroxide ions. However, ammonia is a weak base. The equilibrium forming the hydroxide and ammonium ions lies largely to the left.
Because I don't remember the number. In an ammonia solution, I don't remember how much of the NH3 stays NH3 and how much becomes NH4. We'll calculate it later in the year. I just don't recall.
At any given time, most of the ammonia is in a non-ionized form.
So it's more than 50%, but I don't remember the number. So you okay with weak and strong acids and bases? Okay. So guys, what we need to do now, and this is how we're going to wrap up the day, we need to talk about the acid-base reactions that you need to be able to balance and talk about intelligently. So we're going to go through these progressively, and we are going to start with what are called neutralization reactions. Guys, when we have a neutralization reaction, as the name implies, an acid and a base are canceling each other out. When this happens, it is typically an acid and a metal hydroxide base, and this forms salt and water. And guys, it's at this point that we need to make sure that we're really, really clear about what salt is. NaCl is one of hundreds of salts. And you all had the experience of walking into our stock room and looking off to the left at all of those bottles of salt. Remember? And those were organized by anion, and then they were organized alphabetically by cation, but all of those things in those bottles are salt, because we understand that the word salt just means a positive and negative ion bonded together. So guys, what does this chemistry then look like? Well, the cation in a salt always comes from the base, and the anion for a salt always comes from an acid. Guys, this is going to be very, very important in February. I don't expect you to remember, but a little foreshadowing. In February, we're going to talk about the pH of salt solutions. You dump sodium chloride in water and the pH stays 7. You dump sodium acetate in water and the pH actually goes up. We'll talk about why when we get into this in February. But for guys, for now, here's what we're going to do. Oops. Hydrobromic acid and potassium hydroxide. Predict the products and write the Net Ionic Equation of 3 minutes. Predict the products, write the Net Ionic Equation. The 3-minute clock is not started yet, so let's talk. Your initial response is, oh crap, right? The next thing you do is the most important thing you're going to do. Can I suggest the first thing to do? Write that down. Big. And in the middle of your paper. So that you got space to do this. Just start writing. So guys, again, predict the products, and then write the Net Ionic Equation. When you're finally written the Net Ionic Equation, if you feel so moved, you are more than welcome to say, aha, out loud. Not yet. You're not there yet. Are you there? So guys, join me at the board. I really, really, really want to shortcut this with you, but I'm afraid that if I do, I'm not going to. So guys, looking at these two reactants, can we say together that this is going to be a double displacement reaction? So I'm going to do this a little bit backwards. So guys, bromine is -1, potassium is +1. How many of each do we need? 1. That means one of our products is KBr. Then the other product is the H getting together with the OH and making HOH, which we refer to as H2O or water. Now, guys, at this point, to write the net ionic equation, we need to get rid of the spectators. I was considering doing this first. I'm glad I chose not to. But now let's pretend like we didn't write the balanced equation. Guys, talk to me about why bromide is always a spectator. Why is bromide? Remember, we've got our herd, right? We got our corral. Yeah, bromide is a halogen. Halogens always dissolve in water unless they are bonded to silver, lead, and mercury, and we ain't got any of those. So bromide is always a spectator, and we get rid of it. Talk to me about why potassium is always a spectator. It's a group 1 metal. Potassium is always a spectator as well. At that point, guys, the ions that are actually doing chemistry are the hydrogen from the acid and the hydroxide from the base, and that makes water. Aha. What's the pH of water? 7. 7 is neutral. What is the name of this reaction type? Get it? Guys, anytime a strong acid, this may be worth making note of. Anytime a strong acid and a strong base react together, the net ionic equation will always simply be the production of water from its parts. Now can we all say aha? That was weak. Kaylee, what's up? Mm-hmm. Interesting. Hold on. Keep. Right. Yes, because water, for now, water does not ionize in water. Right, so water is water. So if it's helpful for you to think about water as being water dissolved in water, that's okay. But understand fundamentally what we've done is we've created a liquid. We've taken aqueous ions and aqueous ions and we've created a liquid. That's chemistry. Correct. Right. You guys okay? All right. So guys, the next reaction type that we need to talk about involves solid reactants. Guys, here's a deep thought. I would encourage you to write it down. We are now talking about solid reactants. And the idea is this. Guys, just because a substance is not a strong base doesn't mean that it can't be a good base. Just because a substance is not a strong base does not mean that a substance can't be a good base. As a matter of fact, some of our very, very, very best bases are not strong bases. So it's at this point that we need to remind ourselves what strong means. All it means is what? Completely ionizes in water. Let me give you an example. Aluminum, please do this with me. Aluminum hydroxide. Other than the concern that aluminum may actually contribute to Alzheimer's disease, guys, aluminum hydroxide is a really, really, really good base. But is it a strong base? No, it is not a group 1 or heavy group 2 hydroxide salt. It is not a strong base. But guys, it's a really good base. It is such a good base that we put it in tablets and we feed it to people with stomach acid issues. It's called Rolaids. Because this is the active ingredient in Rolaids. But what makes it such a good base? It's got 3 hydroxides. We call this tribasic. This is a really, really good base. It just doesn't dissolve in water, so it's not a strong base. But guys, let's look at the chemistry that's taking place when you take a Rolaids and it goes down in your stomach and it neutralizes the hydrochloric acid that we call stomach acid. Well, guys, this is going to be a double displacement reaction. Aluminum hooks up with chloride, and it makes aluminum chloride, which is AlCl3. Then the hydrogen hooks up with the hydroxide, and that makes water. Now, guys, I'm not going to spend the time right now to draw a beaker, but we need to talk. Does aluminum hydroxide dissolve in water? Does aluminum hydroxide dissolve in water? How do you know the answer is no? Because it's not a strong base. So, guys, aluminum hydroxide is a solid. And I know we said that we weren't going to draw subscripts. I'm doing this simply to draw the point about what these things are doing. Does HCl dissolve in water? Yeah. Does it ionize in water? Yeah, it's a strong acid. So, guys, these then are our... Is this balanced? It's not. 3... Wait, it's going to balance at 6, isn't it? Oh, hold on. Wait a minute. HOH. That makes this easier to balance. So we've got 3 OHs, 1 OH, so we need a 3. 3 hydrogens, so we need a 3. You guys know that trick, right? If you're balancing waters, rewrite it as HOH. So, guys, we've got this. Then we've got 3 protons. Then we've got 3 chlorides. Then over here, does aluminum chloride dissolve in water? How do you know the answer is yes? Because all halogens dissolve in water unless they're bonded to silver, lead, or mercury, and that's not aluminum. So, guys, this dissolves in water. So we have aluminum 3 plus, and then we have 3 chloride minuses. Now, water is a liquid, so that does not ionize like so. So, guys, what then are our spectators? The only spectator in this reaction is not chlorine. It is chloride. Those are different. Chlorine is a yellow deadly gas. Chloride is chlorine plus an electron dissolved in water. You eat it. It's in salt. It's not a brown deadly gas. The difference is just the addition of the electron. So guys, this then is our net ionic equation. Aluminum hydroxide plus 3 protons yields aluminum ion and 3 waters. That is our net ionic equation. You guys okay? Okay. So gang, we've got 2 more to do. 2 more general reaction types that you need to know. These are what are called the gas-forming reactions. You will get more exposure to this in lab shortly, next week. But guys, these are what are called the gas-forming reactions. One gas-forming reaction is acids bonding with sulfide-containing compounds. Let me make sure I'm using the same example I have in the notes. So guys, we're going to do this. Sodium sulfide reacting with hydrochloric acid. When this reaction takes place, it's a double displacement reaction. One of our products is sodium chloride. The other product is H2S, and then it balances like this. So guys, let's talk about H2S. If you've been to Yellowstone, you've been exposed to H2S. This is hydrogen sulfide gas. It smells like rotten eggs. It's always very many times present in geothermal features. If you've ever smelled that rotten egg smell, that's hydrogen sulfide gas. We're going to make it in lab next week, but we're going to do it in the fume hood because it stinks. So, guys, what we've got to do is this. We've got to kill the spectators and write the net ionic equation. I'm going to try to do this with you quick and clean. Are you okay with the idea that sodium is a spectator because sodium is always a spectator? Are you okay with the idea that chloride is a spectator because chloride is always a spectator? Can we then write the net ionic equation that says sulfur minus 2 plus 2 protons yields hydrogen sulfide gas? That's the net ionic equation. Is that okay? Okay. How do you know what? You need to memorize it. Anytime you see a sulfide salt reacting with an acid, you need to know that that makes hydrogen sulfide gas. You just have to know that. There's one other gas-forming reaction that you need to know. Guys, the other gas-forming reaction that you need to know involves carbonates and bicarbonates. This is the volcano reaction that you did in 3rd grade with food coloring and made volcanoes. Now guys, here's the deal. Maddie asked the question, how are we supposed to know when it makes a gas? This is what you're looking for. Sulfides, carbonates, or bicarbonates. If you have those things reacting with acids, it will make a gas. If it's a sulfide, it's hydrogen sulfide. If it's a carbonate or a bicarbonate, it's different, and we're going to do one together. So guys, let's do this. Let's take hydrochloric acid, and guys, when you're writing this in your notes, go all the way to the left. It goes like this. Hydrochloric acid, and let's do our good friend sodium bicarbonate, which you know to be baking soda. Now guys, double displacement reaction. The H hooks up with the HCO3, and that makes No, stop. Don't write that down. Sorry, we're going to do this better. Let's do that second. So the Na hooks up with the Cl, and that makes NaCl. Can you recover with me? Then guys, the H hooks up with the HCO3, and that makes H2CO3. But guys, here's where this gets tricky. H2CO3, which is called carbonic acid, is very unstable. And what it does is it actually breaks apart. Only this breaks apart into carbon dioxide and water. Now, if you're really paying attention, guys, this is a weak acid, right? Don't write this down, but this is a weak acid, meaning that this should be a double. We're going to go for another minute. This is a weak acid, meaning that it should be a double-headed arrow, but we don't represent it that way. Why not? And the answer is because as fast as the carbon dioxide gets produced, it bubbles away. And so the H2CO3 is always breaking down to replace it. So because the carbon dioxide is always bubbling away, we say that this breaks apart completely, and this then gives us our overall equation. Our products are table salt, carbon dioxide, and water. So now let's kill our spectators, and then we're done for the day. So guys, chloride, let me switch colors. Chloride, always a spectator. Sodium, always a spectator. And guys, what that leaves us with then is hydrogen ion plus bicarbonate ion, yielding carbon dioxide and water, and that should be balanced. And it is. Diana, thank you. You guys good? Okay. So gang, this then is your homework. And we will look at this on Tuesday of next week.